Have you ever found yourself wondering if, the wildest concepts from science fiction could actually jump off the page and into our world? Today, we're taking a deep dive into a topic that has long belonged to that sci-fi realm, but thanks to the groundbreaking work of Jürg Schneppert on quantum entanglement and teleportation, it's quickly becoming, well, the physics of the very real present.
It's true. These concepts are genuinely fine-bending. And what's so remarkable about Schneppert's work is his unique ability to take these incredibly complex quantum mechanics and make them actually accessible, even for someone just sort of starting their journey into this field.
Exactly. That's why we're so excited to delve into this. So our mission for this deep dive is to explore exactly what makes quantum entanglement and teleportation so fundamentally special that they could genuinely change your future. Okay, let's unpack this.
Fundamentally, these two concepts challenge our deepest understanding of reality itself.
Challenge it. In what way?
Well, imagine two particles separated by vast distances, even kilometers, yet they influence each other instantaneously, like as if no distance exists between them at all. Schneppert aptly describes this as spooky action at a distance, a phenomenon that famously perplexed even Einstein.
That sounds utterly bizarre, almost like, magic.
Precisely. And this magic, as you put it, holds immense potential for a technological revolution. Schneppert paints a picture of, absolutely tap-proof communication, quantum computers that would render today's most powerful supercomputers, about as useful as slide rules maybe, and even the very real prospect of a global quantum internet.
Right. It's easy to get lost in those science fiction-like possibilities, but let's ground ourselves first. What exactly is quantum mechanics at its core?
At its core, quantum mechanics provides the description for how matter behaves at the atomic and subatomic level. A central distinction from the classical physics we're used to is this idea of wave-particle duality.
Wave-particle duality. Okay, my intuition is already struggling with that one a bit.
You're definitely not alone. Schneppert illustrates this vividly with the example of the famous double-slit experiment. It shows that particles, like electrons, can sometimes behave like waves, producing interference patterns, which is just classically impossible for a particle. It's sort of as if they can be in multiple places at once or take multiple paths simultaneously.
That's genuinely mind-bending. So particles can exist in this kind of ambiguous state until we observe them.
Exactly. This inherent ambiguity is characteristic of the quantum world. This is where the concept of superposition comes in. A particle can exist in multiple states simultaneously until a measurement forces it into a single definite state.
Like Schrodinger's cat being simultaneously alive and dead until you actually open the box.
A macabre, yes, but a remarkably accurate analogy for the concept.
And through that active observation, this superposition collapses, right? And the cat is then definitively either alive or dead.
Precisely, yes.
Okay. Now, Schneppert also mentions some technical mathematical tools like Hilbert space and bracket notation. That sounds pretty complicated, honestly, and maybe a bit intimidating for listeners.
Well, don't worry. These aren't concepts you necessarily need to calculate with yourself. But it's important to understand why they're necessary. These are merely mathematical tools. They give physicists the precise framework to, manage and predict the behavior of these particles that can exist in multiple states at once. Think of Hilbert space as the conceptual stage where all these simultaneous quantum possibilities can coexist. And bracket notation is simply the language or shorthand they use to clearly write down and track these states and, how they change.
So it's a kind of mathematical secret script, something that allows physicists to make sense of this inherently peculiar quantum world.
One could absolutely say that, yes. It gives them the precision they need to work with quantum uncertainty.
Okay, that clarifies things a bit. But let's return to quantum entanglement. What exactly does it mean when two particles become entangled?
Right. When two particles are entangled, they become connected on a really fundamental level. Regardless of their separation, whether they're meters or light years apart, if you measure the state of one particle, you instantly know the state of the other. It's almost as if they communicate telepathically.
That's truly incredible. And Schneppert highlights this entanglement as the very foundation for something as wild as teleportation. But before we jump headfirst into that, what makes entanglement so utterly unique? And I mean, how on earth was its existence even proven?
Well, its distinctiveness lies in the fact that it fundamentally breaks with our classical understanding of locality.
Locality. I think a lot of us might assume what that means, but maybe define it for us.
Sure. In our everyday world, objects only influence each other when they are close enough to interact physically, right? You push a shopping cart, it moves. Simple cause and effect nearby.
Yeah.
Quantum entanglement, however, demonstrates that particles can remain intricately connected over any distance, which is exactly why Einstein famously dubbed it spooky action at a distance.
But how could something so counterintuitive, so spooky, be experimentally proven? How do you show that actually exists?
This is where Bell's inequalities, as discussed in Schneppert's work, become absolutely crucial.
Bell's inequalities. Okay, that sounds like something out of a complex math textbook again.
They do, a bit, but their purpose is quite profound, really. These inequalities describe how measurement results would behave if the world worked according to classical rules, where properties are local and real even before measurement. Quantum mechanics, however, predicts that these inequalities will be violated, which implies that the world simply does not operate as we would classically expect. It's a direct challenge to our everyday intuition.
That still sounds pretty abstract. Could you maybe illustrate it with a practical example, make it a bit more concrete?
Of course. Let's imagine we have two entangled particles. We send one to Alice's lab and the other to Bob's lab, far apart. At each lab, they perform a random measurement on their particle, let's say, measuring its spin, which can be up or down. Now, classically, you'd expect the results at Alice's lab and Bob's lab to be entirely independent, right? Just random chance at each end. But quantum mechanics predicts that their results will be correlated, and correlated in a way that is stronger than any classical explanation allows. It's almost like the particles know what measurement is being done on the other one instantly, even without any signal passing between them.
Ah, okay, so it's the strength of that correlation that defies classical physics. And these surprisingly strong correlations were then confirmed experimentally.
Exactly, yes. Experiments, particularly those by pioneers like Alain Aspect and Anton Zeilinger, have unequivocally confirmed the violation of Bell's inequalities. This provided, irrefutable proof of quantum entanglement's existence, a truly groundbreaking revelation about how reality works.
Wow, so it's not just some oddity, but a fundamental truth about how reality itself operates at its most basic level. It challenges our very assumption that things must be local to affect each other.
Yeah.
Yeah, profound. But Schneppert takes us even further, describing how this strange entanglement can be utilized to actually teleport information. How exactly does this quantum teleportation work?
Okay, so Schneppert details the process using what's known as the Bennett-Broussard protocol. Think of a protocol here as just a very specific set of steps, like a recipe for how the information gets transferred. In this scenario, let's say Alice wants to teleport the state of a qubit, that's the smallest unit of quantum information, to Bob. To do this, they first need to share a pair of entangled qubits, which they've prepared beforehand.
So it's almost like they have a quantum hotline, a secret connection established between them before they even begin.
That's a great analogy, yes. Alice then performs a specific measurement. She measures her half of the entangled pair together with the qubit whose state she wants to teleport. The results of this measurement are just classical information, like ordinary bits, zeros, and ones, which she then sends to Bob through a regular communication channel, like email or a phone call.
Wait, hold on. How can Bob reconstruct the qubit's state from just this classical information? The actual quantum information itself isn't directly transferred, is it?
You've hit on the crucial distinction there. That's exactly right. The quantum information itself, the delicate quantum state, is not directly transmitted across the space. However, Bob still possesses his half of the original entangled pair, and by cleverly combining his own measurement, which he performs on his entangled qubit, with the classical information Alice sent him, he can perfectly reconstruct the original qubit state on his end. It's as if the information jumps from Alice's original qubit to Bob's qubit, without actually traversing the physical space in between.
My mind is genuinely blown by that. It's such a completely counterintuitive leap.
And it's not just theory. This has actually been demonstrated. Photons, atoms, and even more complex quantum states have already been successfully teleported over various distances in labs around the world. In fact, as Schneppert mentions, satellites have even been used to transmit quantum information over 1,000 kilometers, proving its feasibility over really long ranges.
That's amazing. It still sounds like pure science fiction, but it's literally happening right now in laboratories and even up in space.
Yeah.
Now, before we launch into the vast possibilities of a future quantum internet, which Schneppert puts on the horizon, perhaps we should briefly discuss the applications that are already within reach. What exactly is already possible, or nearly possible, in this field?
Yeah, good point. A very exciting and increasingly critical area is quantum cryptography. This technology enables theoretically, absolutely tap-proof communication, which is, as you can imagine, a huge necessity in our increasingly digitized and interconnected world.
Tap-proof. That's a really bold claim. How could that possibly work? How can you guarantee that?
Well, imagine you want to send someone a secret message. With quantum cryptography, you can create a cryptographic key that's based on the fundamental laws of quantum mechanics themselves. Any attempt by an eavesdropper, let's call her Eve, to intercept or copy this key would inherently disturb the quantum information. Remember the measurement collapsing the state? It's like that. Eve's snooping would immediately change the state of the quantum key, and that change would instantly expose her presence to Alice and Bob. It's literally impossible to listen in without being detected.
That sounds absolutely ingenious, like a perfect security system built right into the fabric of reality itself.
Oh.
And what about the quantum computers Schneppert mentions? Could they genuinely revolutionize our world in the way people talk about?
Oh, absolutely. Their potential is truly revolutionary. Quantum computers leverage superposition and entanglement, these weird quantum properties we've been discussing using qubits, and they use these properties to perform calculations that are simply unsolvable for classical computers today, or would take them billions of years. Schneppert points to Shor's algorithm as a prime example. It could theoretically crack most current encryption methods in an incredibly short time.
Right, but that almost sounds daunting, doesn't it? If these quantum computers are so much faster, couldn't they also be exploited for criminal activities, like breaking all our current cybersecurity?
That's a completely valid concern, and one researchers take very seriously. However, it's crucial to remember that quantum cryptography, the tap-proof communication we just talked about, simultaneously provides the very protection against such attacks. So it sort of creates this continuous race between attack and defense, where both sides are driven by advancements in quantum mechanics. The tools to break current encryption are being developed alongside the tools for fundamentally secure future encryption.
It's a fascinating balance. Okay, so Schneppert even goes further, sketching out the vision of a global quantum internet. How realistic is such an idea, maybe in the foreseeable future?
It's certainly still a long journey ahead, no doubt about that, but the research is making rapid, honestly astonishing progress. Schneppert references those satellite experiments we mentioned earlier. They've already successfully demonstrated long-distance quantum information transfer. That proves the core concept is feasible, at least.
A quantum internet? That truly sounds like something out of a futuristic dream. What exactly would be the profound advantages of having such a network?
Well, imagine connecting quantum computers worldwide. You could combine their immense processing power to tackle problems currently way beyond our reach, things like designing new materials, discovering new drugs, or even simulating complex climate models with incredible accuracy. Or think about enabling truly tap-proof communication across continents for governments, financial institutions, businesses, even individuals. A global quantum internet could fundamentally reshape how we communicate, how we conduct scientific research, maybe even how we live our daily lives.
Wow, that's incredibly compelling. But what are the significant challenges that still need to be overcome to transform this incredible vision into reality? It sounds like a massive undertaking.
It is indeed a massive undertaking. One of the biggest challenges is definitely scalability. We need to develop stable and controllable quantum computers and communication systems with many, many more qubits than we currently have. Hundreds, thousands, maybe millions for some applications. That's essential for complex calculations and for building a truly global network.
Okay, scalability.
Yeah.
What else?
Another major hurdle is error susceptibility and just the sheer fragility of quantum systems. They are incredibly sensitive to the tiniest disturbances from their environment, like heat, vibration, stray electromagnetic fields. This leads to something called decoherence, which is basically the loss of those delicate quantum properties due to unwanted interaction with the surroundings. So developing robust and reliable error correction methods, ways to protect the quantum information and fix errors as they happen, is a central ongoing challenge. It's almost like trying to, keep a soap bubble perfectly intact in the middle of a busy train station. It's really, really hard.
That sounds like a truly monumental engineering feat. But I suppose if these challenges can be overcome, then it genuinely opens up almost unimaginable possibilities.
Absolutely. And Schneppert's work, I think, impressively demonstrates that quantum entanglement and teleportation are not just theoretical curiosities, not just weird physics footnotes. They hold the tangible potential to fundamentally transform our world in the coming decades. It really puts the deep in deep dive, doesn't it?
It certainly does. Thank you so much for these incredibly exciting insights into the world of quantum mechanics. It's truly astonishing how Jörg Schneppert manages in his work to explain these complex topics so, understandably, while also vividly illustrating the sheer fascination and the immense potential of this new technology.
Oh, it was a genuine pleasure discussing this with you. It's fascinating stuff.
And we sincerely hope this deep dive into Jörg Schneppert's work was as enjoyable and enlightening for you, our listener, as it was for us. If you wish to explore this topic further, we highly recommend reading the original publication. And here's something to ponder. Imagine, beyond just communication, what teleporting information without any physical travel could imply for our very understanding of connection, distance, and maybe even reality itself. Perhaps we're only just beginning to grasp the true depth of the universe's interconnectedness. Until the next deep dive.